Okay, so last week, this is week 5, day 2. If you look at the lecture notes, we evaluated this integral. This is the dipole potential. We took the gradient and then integrate over a spherical volume. So that's basically what we said. If we can prove this step, we are done. This is the proof. So you can just go over them. Well, it's kind of straightforward, but you have to do some tricks, a couple of tricks. It's long, and it doesn't really give you much. So I say it is 4 pi over 3 times the polarization vector, which is the vector over here. This one, this vector over here, P. Put the minus sign, because the electric field is the gradient, we have the minus sign. So at the end, we see that this integral is equal to minus 4 pi over 3 times the polarization density. Now, there is one catch. I made 2 mistakes, which at the end I obtained the results. The result is correct, nevertheless. The problem is, you see, I took this derivative out, this gradient out. There is a catch in taking that gradient out. Okay, the derivative is with respect to r, not with respect to r double prime, so I can say that I might be able to take it out, but v prime depends on r. As I change v, because v prime is a sphere located around r. So I shouldn't actually take that gradient out. It should stay inside. Now, to evaluate this, I mean, at least our previous derivation, the gradient is already inside, so no problem with that. So this result is correct. Strictly speaking, this expression in this form is not correct. The gradient should be inside. But in this form, I can take it out because I'm eliminating the dependence on the volume, on the domain on R. So this final result is also correct. And by the way, this final result is the result of Greiner also. Although I don't agree with some of the steps that he did. So this is our final result. Well, basically, this integral over here is now nothing but the average potential, or the macroscopic potential. That's, I mean, from now on, we will not be writing these average values, but we will just say this is the macroscopic electric field. We will always be dealing with the macroscopic electric field, not the microscopic details. And then one more step that we can do to interpret this result is, let's say V of R is equal to d cubed R prime, rho of R double prime divided by R minus R double prime plus P of R double prime dot R minus R double prime divided by R minus R double prime cubed. The first term is basically what we expect. It's the charge density, local charge density, average over a somewhat a large size, plus a term that is due to the polarization of the due to the dipole moment. It can be either there, already there, or it can be created by external fields, etc. But if there is a dipole moment, then it is the second term. Now, one thing that you have to distinguish is the dipole moment is already created by the charges. But the charges that are separated from each other in the microscopic scale. So on the average, those charges do not contribute to rho. So let us make an example. Okay. So I have my, let's say, dielectric, not a conductor. I put a charge inside. So it will create an electric field, let's say positively charged. Well, the electrons will, it's made of a conductor, the electrons are not free to leave their atom, but nevertheless, if I put a positive charge somewhere in my material, negative charges will be slightly attracted to my positive charge, and the nuclei will be repelled from the nuclei. So even if I have a neutral atom, the charges separate slightly. Well, the atom is neutral, so they do not contribute to this rho. Nevertheless, the charges are slightly separated. They create this dipole density, this polarization. Now, of course, this separation does create a local charge density, local fluctuations in the charge density, which we can make more explicit. Let's look at that term, that last one. D cubed r prime, p at r double prime, r minus r double prime, divided by r minus r double prime cubed, which is equal to d cubed r prime, p of r double prime, times the gradient with respect to r double prime of 1 over r minus r double prime. There's no minus sign, by the way, here, because r double prime in the first line already has that minus sign. Well, this is equal to d cubed r prime divergence of p r double prime divided by r minus r double prime minus 1 over r minus r double prime times the divergence of p. This is the potential due to, let's say, the polarization. I just kind of, I'm using the product rule, which is equal to the surface integral, the integral over a volume of a divergence. I can always convert it into a surface of p divided by r minus r double prime and minus d cubed r prime 1 over r minus r double prime of the divergence of p. This is a integral over the volume. This is an integral over the boundary of the volume. Which, by the way, just looks like this expression over a surface sigma. Let's say the surface coordinates are double prime sigma at r double prime divided by r minus r double prime. Let me call this sigma b, plus d cubed r double prime rho b of r double prime divided by r minus r double prime, where sigma b at r double prime is nothing but p dot n n is the normal vector to the surface, pointing from inside to outside, and rho b at r double prime is equal to minus the gradient divergence of p. So basically, you can interpret these things as the charges that are already bound to the atoms. In the atom, so they are not free. We didn't put them. They are not free to move around. So on the average, they give 0. But their effects are felt through the polarization, P. B meaning bound charges. They are not the charges that are free to move around. They are bound to the atoms, they are bound to the molecules.
How would this be noted? I'm having difficulty imagining how this could be noted.
Let's do some simple examples. Not computation, but mainly in our understanding. Let's see. For example, we have our dielectric. As I said, I put some charge over here, let's say plus Q charge. Then, of course, this will cause the electrons and the atoms to, electrons and the nuclei. Electrons will be moving towards my positive charge. The nuclei will try to move away from the nuclei. Of course, they cannot move freely, but they will be slightly shifted towards my positive charge or away from my positive charge. So if you look at each one of the atoms or molecules, they will look something like this. Negative charges are close, positive charges are further away. Negative charges are close, positive charges are away. Negative, positive, negative, positive. So let me enlarge our section. So here we have a dipole, here we have another dipole, and this side is slightly more positive. They contain slightly more positive charges, and this side contains slightly more negative charges. Now, if these two dipoles have more or less the same dipole moment, so that will basically mean, so here we have the minus, the plus charge over here and the minus charge over here, the plus side of one of the dipoles and the minus charge of the other dipole, they will more or less cancel each other. And eventually I will end up having zero charge inside. This is assuming that all the atoms or molecules are polarized by the same amount. That is uniform polarization. When I have uniform polarization inside my material, I won't have any charges. I won't have any bound charge. Well, let's look at over here. If P is constant, the gradient divergence of P is 0. Well, if P is not constant, well, that basically means that the polarization changes. Let's say this atom is more, the lower one is more polarized than the above one. That is, P is decreasing. Well, here on the average, I will have more positive charges because the positive side will be more positive than the negative side of the other dipole, assuming the polarization is not constant. It is decreasing. So the charge will be positive. Well, if P is decreasing, the divergence will be negative, and minus that one is positive. So effectively, we have a positive charge density over there due to this polarization of the atoms. We can do the same thing on the surface. Well, let's see, we have these dipole moments. Let me take this part, enlarge it a bit. This is my surface. And I have this polarization. So this is negative, this is positive. Well, this negative charge in the bulk, if the polarization is uniform, it will be cancelled by the positive polarization of the other dipole, the neighboring dipole. If it is not uniform, it will contribute to the bulk charge. But on the surface, there is a positive charge. So this is a case in which the polarization of these dipoles are in that direction. That, remember, the polarization vector points from the negative to the positive charge. So the polarization vector points out of the surface. So if you take the polarization vector, multiply it with the normal direction, you get a positive number. And the bound surface charge density, hence, is a positive number, as it should, from this physical interpretation. So this is why the polarization, if it's not uniform, it does actually correspond to a charge distribution. But a charge distribution that we didn't put there. A charge distribution due to the motion of the atoms. motion of the charges inside our atoms. Well, then we can go ahead and calculate the curl and the divergence of this electric field. Curl of the electric field will always be 0. You see, although this electric field is the average electric field, we had just seen that it can be actually written down as the electric field created by, let's say, so-called free charges plus the bound surface charge plus the bound bulk charge. And this bound surface charge and bound bulk charge is basically the electric field created by the dipole moment. So it's still the electric field created by some charge density, and hence the divergence of this average electric field is 0. Then comes the because it's actually the gradient of something. So that's why the curl is still 0. But the divergence of this electric field would be equal to 4 pi, this time rho plus rho bulk plus sigma bulk with suitable Dirac delta function. Now this rho bulk and sigma bulk themselves create some kind of an electric field. Just themselves. So we usually define what is called the polarizability, the displacement field as rho bulk plus sigma bulk. Well, this is the kind of, you can think of it as the electric field created by these charges up to this 4 pi coefficient. So that's probably one of the reasons why it's called the displacement field. No, sorry. Again, this is not the displacement field. We call this this P field, polarization field. This is kind of the definition, so that the divergence of electric field minus 4 pi, this P field, is equal to 4 pi rho. And this is what's called the displacement field. Divergence of the displacement field is equal to 4 pi times rho. Let's call it free. Now again, this rho F or rho free is basically the charges that we put by hand, or it's not the charges that are connected to the atoms. These are basically the equations we have for the electric fields in matter, these two. Then, of course, to proceed further, we need to know the properties of the matter. Now, can you check that my convention is consistent with the books? That P is not the polarization, but does it use a different symbol? No, it's P, yes. 4 pi P. Well, it has a minus sign in the definition. This is minus, right? In the definition of the book. So this is plus. Now this P you can basically think in terms of the electric, kind of an electric field created by this polarization of the medium. Related. I mean, it's not exactly equal to, there's the 4 pi factor, the minus factor, as you said. Now then the problem is, okay, the second equation is easily solved. The second equation basically tells me that tells us that the electric field is minus the gradient of some potential. But how do we put the electric field in the first one? Now D will basically be a function of the electric field itself. If the electric field is 0, it should also be 0 because there won't be any polarization, unless we are talking about some special materials that keeps their polarization even in the absence of electric fields. But for most materials, when the electric field is 0, the D field will also, the polarization will also be 0, this P field, and E is 0, P is 0, so D will be 0. So if you write them in terms of components, the X component of this D field will be, it can be proportional to the X component of the electric field, to the Y component of the electric field, and the Z component of the electric field. Of course, there will be additional corrections proportional to the square of the electric field, to the cube of the electric field, etc. For most materials, we can just ignore those squares and cube terms, and we end up having what we call the linear dielectrics. So D is linear, depends linearly on the electric field. And similarly for the Y components. And also for the Z component. Now, it is possible that when you apply an electric field in one direction, the electric field in the material, which is the displacement field, might be pointing in another direction. They don't have to be parallel in general. That is basically because you see this so let's look at this expression. This is the potential. You take the gradient, you obtain the electric field. You don't put any charges in your material, you just put it in an electric field. So rho is 0. Then there's this polarizability of the material, this dipole moment density. And this dipole moment density is basically the relative displacement of negative and positive charge, the electrons and the nuclei relative to each other due to the applied electric field. But for example, if you have a crystal, which is nothing but a layered material, it might be possible that the charges move more easily on a layer, but they might not be able to move so easily in multi-layer to the other layer. Well, that would mean that the polarization, whatever the direction of the electric field is, the dipole moment will be larger along along one layer. So you apply an electric field in this direction, the charges are displayed significantly along the layer, but only slightly in the interlayer direction. So P would be, although this is the electric field, P will be in some non-parallel direction. And hence, this D field, the displacement field, will also be not in the direction of the electric field. In general, they don't have to be in the same direction. But most of the time, for simplicity, we assume isomorphic materials, isomorphic dielectrics. And so for isomorphic dielectrics, isotropic, sorry. And it's the same in every direction. So if it's isotropic, the created dipole density will be in the same direction as the electric field, so the displacement field will be in the same direction as the electric field. For isotopic dielectric, epsilon ij will be proportional to Kronecker delta ij. So D field will be equal to epsilon times the E field. Of course, this is in linear isotropic dielectric. Linear because we are ignoring the squares and the cube terms. Isotropic because it's the same in every direction. Now we are in research, especially if you are interested in optics, you have probably heard of the nonlinear optical materials. Now, what they mean by nonlinear optical materials is basically that this linear approximation is not enough. So you have to go to higher order terms. Either in the linear approximation, epsilon is very small, or they create very large electric fields. So the ignored terms in a linear dielectric are no longer negligible, so you have to keep them also. That gives you a nonlinear material, nonlinear dielectric. And as I said, these layer materials, most of the time, they are not isotropic, so you cannot use this relation. But for these materials, kind of the equation is easy. So the curl of E is 0 anyway, and the divergence of D will be equal to 4 pi rho. And D is equal to divergence of epsilon times E is equal to 4 pi rho. Furthermore, you see, isotropic doesn't mean homogeneous. So epsilon can still depend on position. So if the material is homogeneous, epsilon times the divergence of E is equal to 4 pi rho. Or the divergence of E is equal to 4 pi over epsilon times rho. Now, epsilon is called the permittivity. Well, basically, nothing changes. Instead of the charges, nothing changes from the free case. You just replace the charge by charge over epsilon. So the electric field would be nothing but before it was just Q over R. Now we have this 1 over epsilon. Q over R squared in the R hat direction. That's the electric field. Not so interesting. So how can we create a simple non-homogeneous system? So we have these two medium. Both are dielectrics. Both are locally isotropic, let's say. This system is not isotropic as a whole. But locally, we can say that the system is isotropic. But it's not homogeneous. There is a boundary, and this permittivity is different in the two regions. Let's assume we put a charge over here. What will be the electric field everywhere? Let's calculate the potential everywhere, not the electric field. What do you say? Q over R, potential. R squared. We are talking about potential. Well, let's look at the certain limits that we know. For example, these two dielectrics, we can choose them to be identical. We can choose epsilon 1 to be epsilon 2. We already know the answer for that case. It's just Q over epsilon times R. Does this reduce to that result in that limit? When epsilon 1 is equal to epsilon 2, is this equal to Q over epsilon times R? No. The second limit we have, let's say this is D. Well, if D is very large, and we are looking at the electric field, let's say in region 2, then region 1 shouldn't have any influence whatsoever. It's very far away. So that is another limit that we know. So we can test our answers based on those limits.
D is so small, it's too small.
If D is very large.
If D is very small.
Well, that I don't know. We have to evaluate it. But at least two limits that we are sure about the answer. So those limits we can test.
And what do you expect to be a factor that changes the potential if D is small?
I don't know. I mean, the potential will be complicated. We have to solve and find it. I don't have any expectation for the time being. Well, let's look at this material. What happens if epsilon is infinite? Electric field goes to zero. It acts like a conductor, right? So that's another limit we know. For example, if epsilon 1 goes to infinity and epsilon 2 is 1, well, that's the charge in front of a conductor. Does that ring any bells? I mean, maybe it's not infinite, but we might try something, image charges, for example. We tried image charges. So first, let's try to understand physically what's going on. We have this dielectric material, we put a charge inside. So just for the sake of demonstration, let's assume that it's a positive charge. Now, the positive charge will attract all the negative charges to itself, and hence creating this polarization of the medium. It will polarize the medium. And so if you look at the second material, it will have some dipoles. Which will look like this. The first medium, it will have dipoles, which will look like this. So basically, since the medium, forget about the homogeneity, let's say it looks as if the first medium, where the permittivity is epsilon 1, if you just imagine the surface will look as if it is charged, just like a conductor. Do you agree? And the positive charges, there will also be some positive charges exactly on the surface due to this epsilon 2. So let's say if epsilon 1 is larger than epsilon 2, that is the first medium is more polarizable, the net charge at this interface will be negative. So it will be as if I have some negative charge on the other side of the this plane, at least in region 2. For a charge in region 2, it will see the charge, the plus Q charge. It will also see the, assuming the first medium is more polarizable, it will also see this negative surface charge in the interface. So that is what a charge over here will see. Right? So one guess could be that, okay, in the case of the conductor, this surface charge acts like an image charge on the other side. We can. We just have to prove that our assumption is correct. But that is what the method of images is about.
We can say that we have something like a conductor.
Yeah.
We didn't assume that one of them is anything.
If
We didn't assume that one of them is anything.
one of the mediums.
Yeah.
Well, then we will have a hard time. So because we have two boundaries we have to take into account. So that's why I am assuming infinite medium. Well, if you have not infinite but very large medium, again, you can just make the approximation of infinite medium. So you see, for an observer over here, it will see this Q charge and Q prime charge. That is my claim. That is still to be proven. So V in region 2 will be equal to 1 over epsilon 2 Q over R plus the distance from the positive charge plus 1 over epsilon 2 Q prime over R prime. I don't yet know what R prime. I don't know. I mean, I'm assuming that is exactly on the other side, but I could have just let that distance to be free and see if it will be satisfied. V1. Well, let's test it a bit. So what do we know in region 2? First of all, it should satisfy this equation, the Laplacian of V at a given, in a region where epsilon is homogeneous, that's a constant, should be equal to minus 4 pi over epsilon rho. This should be satisfied. Laplacian of V2 in region 2 is equal to 1 over epsilon 2 Q times the Laplacian of 1 over R plus 1 over epsilon 2 Q prime times the Laplacian of 1 over R minus. In region 2, this is equal to, well, in region 2 this is 0. It's a Dirac delta on region 1. But in region 2 that Dirac delta is always 0. And this is minus 4 pi over epsilon 0 Q times Dirac delta, 3-dimensional Dirac delta, R minus delta plus. Okay, let me fix my notation a bit. Okay, this is what I call R plus. This distance is what I call R minus. The position of this charge I will denote by delta plus. The position of this other charge is what I will call delta prime. And this position is delta, or R. It's at the point R. Okay, so it does satisfy the Poisson equation in that region. Epsilon is equal to epsilon 2 in that region. It satisfies that condition. It satisfies the boundary at one of the infinities. Still, I have to make sure that it satisfies the boundary condition in the interface between these two regions. That is still to be determined. Now, the boundary conditions at that interface, to test those boundary conditions, I have to also look at find the potential in region 1. Let's say in region 1, you only see this surface. And that surface kind of mimics a charge, that's my claim, at the position of Q. So I will just assume that, okay, maybe it will also see Q, but at the same point there is this, the image created by the surface charge, so the total effect will be just a charge of Q double prime. Well, you see, in region 1, what are the charges that we will observe? We will see the charge Q. We will also see the surface charge. My claim is the surface charge also behaves as an image charge at the position of Q. So what I will be observing is a total charge of Q double prime at the position of Q. That is my claim.
Q double prime replaces Q prime?
No, Q prime is not there. You see, Q prime is the charge that when the observer sees in region 2 because of this surface charge. Okay? Now, when I'm in region 1, the observer is in region 1, it will see the surface charge, but this time it will create an image on the other side, so in region 2. When I'm in region 1, the image will be in region 2. When I'm in region 2, the image will be in region 1. Okay?
So Q double prime has the same position as Q?
Yes. Q double, I'm just making up for the time being. And if the potential I have satisfies all my equations and the boundary conditions, I'm done. In region 1, V1 will be 1 over epsilon 1 Q over R plus. Because R plus, what I call R plus is my distance from the Q charge that I put over there. Q double prime, of course. And just take note, the potential in region 1 has this factor 1 over epsilon 1, independent of where the charges are. And the potential in region 2 has this factor 1 over epsilon 2, no matter where the charges are. So you see, in region 2, this V2, this has epsilon 2 factor, not epsilon 1, although the image charge is in region 1.
The surface, the polarization, we put some charge on the surface, which will compensate for the effect of epsilon in the first region. Right?
Well, I prefer to think of like this. If you have an image, a mirror, let's say, what you see in the mirror is your domain. not what is behind it. Also, if you just take the other limit that epsilon goes to infinity, you see when epsilon 1 goes to infinity, V1 should be 0. And if we have this 1 over epsilon 1, that's a guarantee. When epsilon 1 goes to infinity, V2 should still have these two terms, both the first one and the second one. So if I had put epsilon 1 over there, it would have diverged. It doesn't really make too much of a difference because we still didn't define Q prime. I can define, for example, it might turn out that Q prime is equal to epsilon 2 over epsilon 1 times something. Then epsilon 2's will cancel, I have 1 over epsilon 1, nothing to do. Now the boundary conditions. First of all, curl of E is always 0. This means that the perpendicular component, the parallel component of the electric field parallel to any surface, this should be 0. This would be continuous. Well, this basically means that V is continuous. V should be continuous, the potential. So let's see, 1 over epsilon 1, Q double prime over, well, when we take a point at the interface, R plus and R prime, they are equal. Divided by R plus should be equal to 1 over epsilon 2 times Q over R plus 1 over epsilon 2 times Q prime over R plus. All the distances from the image charges and the real charge, they are equal to each other on the interface. In the interface is in the middle. So these I can cancel. So this is one relation I have. Epsilon 2 times Q double prime should be equal to epsilon 1 times Q plus Q prime. Well, again, we can just consider the limit as if epsilon 1 goes to infinity. If epsilon 1 goes to infinity, for this relation to be satisfied, Q plus Q prime should be 0. The image charge is minus the real charge. But if Q is equal, Q plus Q prime is 0 to start with, the right-hand side is 0. So Q double prime should also be 0. So in region 1, there are no electric fields, no images. Then we have the divergence of D. This is equal to 0 on the boundary. You say divergence of E is non-zero on the boundary because we have these bound charges. But divergence of D is 0 because the divergence of D only is proportional to the free charges, the charges that we put. Divergence of D is non-zero only at the position where we put the charge. But this basically tells me that the change in the perpendicular component of D across the surface, this should be 0. Do you agree? Now you see, if you remember beforehand, we had the divergence of E was equal to 4 pi rho, and from which we concluded that the electric field outside the surface minus the electric field inside the surface was equal to sigma over epsilon 0, 4 pi sigma in the normal direction from inside to outside. Well, this expression is more or less identical with no charges. So it says that the change in the perpendicular component, because you see the change is proportional to the perpendicular component, the horizontal component has to be continuous. The change in the perpendicular component should be 0 because there are no free charges on the boundary between these two media. Well, now we need to calculate that. I'm kind of feel lazy to do it. Well, let's see. X, Y, and Z. V1, we said that this was equal to Q double prime over 1 over epsilon 1 Q double prime over R plus, which was equal to 1 over epsilon 1 Q double prime over R plus is x squared plus z squared plus y minus d squared, everything under the square root. Remember, y is a negative number. So that y minus d squared is larger than y squared. Do you agree with this one? E perp, the perpendicular component is minus derivative of the potential with respect to y. Y is the perpendicular direction. And this is equal to 1 over epsilon 1 Q double prime times y minus d divided by square root of x squared plus z squared plus y minus d squared, 3/2. And the perp in region 1 on the boundary is just y is equal to 0. So this is in region 1, this is epsilon 1 times E perp in region 1 on the boundary. This is equal to Q double prime minus d over square root of x squared plus z squared plus d squared. Q 3/2. Now we need to do the same calculation in region 2. V2, remember this is 1 over epsilon 2 Q over R plus 1 over epsilon 2 Q prime over R plus Q prime over R prime. This is equal to 1 over epsilon 2 Q over square root of x squared plus z squared plus y minus d squared plus 1 over epsilon 2 Q prime over square root of x squared plus z squared plus y plus d squared. Remember, Q prime was on the other side of the surface. And D2, the displacement field in region 2, the component perpendicular to the surface on the boundary, becomes, well, to obtain D2, we multiply epsilon E by epsilon 2, and what remains is Q times minus D divided by square root of x squared plus z squared plus d squared to the power 3. Here I don't have 3 halves, it's just the 3. The half is already in the square root. And plus q prime times d divided by this square root, the same square root cube. And these should be equal. So here I have q double prime multiplied by minus d should be equal to q minus q prime. Now, you see, q double prime is multiplied by minus d also. So I'm factoring out minus d. This is one relation we have. The other relation between q and q prime was this one. Now let's solve them. Epsilon 2 times q minus q prime, this is equal to epsilon 1 times q plus q prime. So epsilon 1 plus epsilon 2 q prime is equal to epsilon 1 minus epsilon 2 q. Q prime is equal to epsilon 1 minus epsilon 2 divided by epsilon 1 plus epsilon 2 of q. Let's check the limits. One limit that we knew was if epsilon 1 goes to infinity, then the image charge should be minus the real charge. Well, if epsilon 1 goes to infinity, q prime is equal to q. A sign mistake. So where did I make that sign mistake? Here, this is minus, this is plus. I moved q prime This is the correct solution. So if epsilon 1 goes to infinity, indeed q prime is equal to minus q. Well, we also have the other limit. If epsilon 1 is equal to epsilon 2, then q prime is 0. There is no image charge. Both the mediums are equal. That is what at least those two limits are satisfied. Now let's look at the other region. Q double prime is equal to, let's see, we said that q double prime is q minus q prime. Q minus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 times q. Q double prime, this is equal to, well, epsilon 2 is cancelled, twice epsilon 1 divided by epsilon 2 plus epsilon 1 times q. Now again we can check certain limits. For example, when epsilon 1 goes to infinity, the first medium is a conductor. Then q double prime is twice q. Well, there's no problem with that because you see the potential in region 1 is proportional to 1 over epsilon 1. So it's enough for the Q double prime charge to be finite. So since we also have the 1 over epsilon 1 in the definition of the potential, Q double prime is finite, so the potential in region 1 goes to zero constant. And the other limit when epsilon 1 is equal to epsilon 2, you see Q double prime is just equal to Q. If both mediums are the same, so if you are in region 1, you just see the Q charge. So that's also what we expect. Now, another thing we can, so what we can derive from these relations, for example, if you look at Q prime, the sign of Q prime depends on the permittivities of different media. If the permittivity of region 1 is larger than the permittivity of region 2, then the electric field, then the image charge is negative. So epsilon 1 is larger than epsilon 2, the image charge will be negative. So it will basically look like this, the electric field lines. But then after this point, they will be mainly straight. And in fact, they will be, you see, in that region, it is as if we have a single charge at this point, so it should be like this. These are our electric field lines. We can look at the other case when epsilon 1 is smaller than epsilon 2. But that is, if epsilon 1 is smaller than epsilon 2, then image charge is positive. So we have some positive charge here. The image charge itself is also positive. So in that case, the electric field lines will basically look like this. And then after this point, straight. Because if you are in region 1, oops. So, questions? We are already over time. You see, in region 1, you also only see one charge, 1 point charge. So that's why the electric field lines of that 1 point charge is straight.